Hello everyone, my name is Karin Wolff and I'm here to talk about my PhD research on engineering problem solving. I'm going to talk about what it looks like in the real world and what this means for the curriculum. Now take a moment to consider the complex challenges facing our engineering professionals in the 21st century. The truth is that real-world problems are messy and complex. Now, given the statistics on our inability to retain and adequately prepare the engineering problem solvers we need, the question in this research is, what does problem solving really look like, given that complexity? Now, the contention is that we have an inadequate understanding of the nature of and relationship between different forms of disciplinary knowledge in 21st century engineering problem-solving practice. Now, so the research looked at how practitioners in the field of practice in different engineering disciplines apply the different engineering disciplines in a real-world problem in different industrial contexts. The aim was to understand what this disciplinary navigation looked like, so that we're able to look back at the curriculum and our teaching and shape it more appropriately for the 21st century. The research is theoretically located in the sociology of education, in the field of recontextualization, and it draws on two key theorists, Basil Bernstein and Carl Mayton's legitimation code theory. Now, I'm looking at the relationship between the different core disciplines underpinning multidisciplinary engineering, their different organizing principles, the fact that on their own these disciplines require different ways of thinking. But what does this mean when they come together in a problem-solving moment? Let's take a look at some aspects of the organizing principles. Now, the engineering region at the heart of this research is mechatronics engineering, and its core disciplines of physics, maths, and logic. I've arranged the key elements of a mechatronics curriculum as a Venn diagram to show this different core disciplinary spread. Now, in Bernsteinian terms, here on the right, we have the traditional physics-based engineering regions, mechanical and electrical, and these are regions underpinned by physics, what Bernstein terms a hierarchical knowledge structure, where we have specific concepts strongly sequenced that absorb lower concepts. Ohm's law is an example, or force. Now, in the center, and applying across the spectrum, is mathematics, a strong horizontal knowledge structure. This simply means there are more mathematical languages or different mathematical languages which you could apply to the same phenomenon. Each language has strong concepts or rules that are not necessarily applicable to a different mathematical language. Now, in the upper left, the regions are underpinned by logic, the disciplinary basis of programming or control systems. Now, this is a weak horizontal knowledge structure. Weak meaning there are choices that are context dependent, like languages themselves, or social science. In other words, the phenomenon itself does not dictate the knowledge form in the way that motion is governed by Newton's laws or voltage is governed by Ohm's law. These kinds of knowledge are weak in that they borrow concepts and rules across families of the same type. They're constantly changing. Things become redundant. So the question is, what does it look like when these different kinds of disciplinary knowledge come together in a problem-solving moment in a specific context? Now, the tool used to look at the problem-solving process comes from one of the legitimation code theory dimensions of specialization, and specifically the concept of epistemic relations. Now, this is about the what and the how of knowledge. The vertical axis is about the phenomenon in question, how strongly it is bounded by recognizable and legitimate principles. In other words, principles that the field holds to be legitimate. The horizontal axis is about ways of approaching the phenomenon. The stronger the rules, the stronger the so-called discursive relations. Now, this epistemic plane gives us 4 codes, 4 ways of thinking. The top right is purist, recognized principles and associated procedures, such as those that you would use when you were dealing with voltage problems underpinned by Ohm's law. Very fixed disciplinary base, very fixed ways of dealing with the problem. The bottom right is recognized methodologies. Doesn't matter what the phenomenon is. It's like following a formula, the structure of an experiment, or applying lean manufacturing rules, or mathematics or economics. Now, the top left is called situational insight. There are many possibilities for addressing the same phenomenon, like choosing a new cell phone, for example. What I want it to do is fixed. The phenomenon is strongly bounded, but how I do it, in other words, which type of cell phone I'm going to choose, is variable. The lower left quadrant is where there isn't a strongly bounded phenomenon or any fixed ways to do things. This could either be because we're now not focused on knowledge, but on knowers, for example, where other things count. Or it could be because there is no legitimate or recognizable phenomenon or practice associated. It's kind of a comme ci, comme ça, laissez-faire situation. Now, each of the knowledge structures that you saw in the previous slide, and each of these insights represents a kind of code, a way of thinking. Each code or insight is significantly different. Now, how did I use this? Very briefly, I had 50 volunteers working as mechatronics technicians or technologists in 3 different types of automation environments. They completed a questionnaire describing the context, the most recent problem they faced, and a technical description of how they solved that problem. I then conducted 18 reenactment interviews. This means they took me through the problem with the actual artifacts in the actual problem site at their companies. The third phase involved getting their supervisors and my industry experts to verify the analysis. I used the epistemic plane to map their approach to and analysis of the problem and the subsequent synthesis of a solution. In other words, I tried to surface the disciplinary basis of their problem-solving process. I'm going to jump straight into a few findings before I show you 2 specific examples. Now, problem-solving patterns emerged in relation to the different components of the problem-solving system. The scale of the environment, for example, dictated a preferred insight, a specific way of thinking. The larger the company, the more doctrinal the insight. The more holistic problem solvers, for example, in the different environments, displayed an anomalous high academic achievement in both mathematics and the logic-based subjects. Each of the environmental types revealed a specific or a problem-solving process pattern. And with regards to the problem structure, in all cases, there was a multi-layered cause-effect relationship between the disciplines in the actual problem structure in relation to a particular problem context. I'm going to now focus on 2 case studies which demonstrate the impact of context on solving the same kind of problem. Now, the first case comes from the contained systems category. Now, these are standalone devices, and our practitioners tend to work in research and development environments, or, in the example I'm going to show you, in maintenance. These are usually micro to very small businesses. Now, in this case, our technician works in a local, highly specialized medical device company. The actual research and development and manufacturing of these devices takes place in Europe. Now, A4, our participant, is the only case study that looks like this. Now, the problem he had to solve was a faulty medical device from a national clinician. Now, he approaches the problem starting in the bottom right quadrant with a fixed methodology. There's a standard procedure. Call the clinician, determine who he is, But in this practitioner's case, the focus is really on set this person's mind at ease that help will be forthcoming. That's the first part of the analysis. Who am I dealing with? What are his or her circumstances? This leads to an analysis of the situation. What part of the country is this? What are the environmental factors? What is, in fact, the actual problem? The third phase of the analysis is the artifact itself, which had to be couriered to the company, and which is mostly the procedure. Now, through these phases, the actual discourse changes. When it comes to the engineering underpinning the medical device itself, the analysis is thoroughly scientifically informed root cause analysis. This leads to a solution, in this case, which is simply doctrinal. The device was being charged incorrectly. It led to the swollen battery, which jammed the opening and closing mechanism. It's a very simple problem, but it's a lovely problem which really highlighted different stages of the problem-solving process and the different discourses used and the different kind of ways of thinking that were required at different stages. Now, this is a company in which human lives are at stake. These are medical devices for infectious disease control. People come first, but it is coupled with scientifically informed and technically sound technologies. Now, what was really interesting at this company was that their values are echoed in the environment itself. The reception area leads into an open, communal, knower-orientated space. This area is visible through glass partitions to the surrounding, more dedicated management and training spaces. Now, the management here deal with different kinds of situations which require them to think of what are the different possible approaches here. The training occurs in this purist-orientated space, in a specific venue, where the signage implies an allegiance to the principles underpinning both scientific and humane practices. There are posters on the walls showing real-world case studies, but also scientific and technically detailed descriptive posters and procedural information. Now, the core business of this particular company is actually device maintenance, and this is set aside in a doctrinal wing with explicitly signposted and sequenced venues that accommodate a natural workflow. The arrangement of this wing was in fact initiated by the practitioner himself, and each of the areas of this company as a whole enables explicit code shifting by virtue of its position, its content, and its signage. So in this case, we see what we call a code match between the actual practitioner and his working environment. Now let's contrast that with something in large-scale manufacturing. This is our third category, the distributed systems category. Now here we have a company in which each aspect, from the design to the manufacture and distribution, is done under one roof with over 200 employees and a host of clients and suppliers all over the world. Now the focus here is on production processes and the delivering of thousands of components to a large number of clients. This is a Six Sigma company with highly regulated, in other words, doctrinal processes and procedures in place. That's their orientation over there on the right. Now, our practitioner is actually a more situationally orientated practitioner. He prefers trial and error. He's very experimental. However, as is the company rule, he sets about solving his problem with a set procedure, a standard Six Sigma improvement approach. He describes the root cause analysis of the process of the problem in his system. The problem is very basically he's getting incorrect voltage readings. And it took him 3 days to solve this problem. He started at one end, replacing and testing each of the components in his system as a whole. In other words, he worked on the right-hand side of the epistemic plane. If, however, he had followed his natural inclination and just stood back to observe all the possibilities, in other words, if he took on his kind of naturally orientated situational insight, he would have asked himself, why are these LEDs, they're little lights like you get on your remote control, getting brighter and dimmer, brighter and dimmer? That would have been a clue to the problem that this was an analog versus digital signaling problem. Secondly, if it looked at the documentation, which people produce, by the way, and people supply, he would have seen that they simply supplied the wrong component. But the supplier is a highly reputable international supplier. He knew that the supply company had been taken over by the less experienced owner's son. But he, and I quote, assumed it was meant to be like that. European machine suppliers think they're of a high standard. Now, this assumption of the reliability of new components or equipment and their documentation is proving to be one of the greatest challenges in engineering problem solving. It emerged across the cases. Somewhere in the more complex system, an operator, a supplier, or a stakeholder, or a colleague is responsible for a decision that leads to an error. All these challenges situated here in the lower left quadrant, and it is these that the practitioners are least equipped to deal with, particularly in large, doctrinally orientated engineering environments. There is an assumption that people in the system need to behave as procedurally and reliably as the inanimate objects in that system. Now, we've seen two different environments. We've also seen a very neat methodology designed to look at complexity. If we zoom back out again, though, we get a potentially messy picture. And as educators, we try to order this. We separate these messy areas out into the curriculum structure with which we're all familiar. However, when our students face that messy capstone project or the real world, the picture is very different. We cannot hope to prepare our students for all the variables in the real world, but we must begin to prepare them for actually explicitly recognizing different kinds of disciplines and negotiating those boundaries. Okay? We need to recognize that the different disciplines imply different ways of thinking. We should enable explicit code shifting between different ways of approaching different phenomena. We need to enable our students to develop a more conceptual grasp of the reality and principles of different engineering contexts. Practically speaking, we need to consider how we allocate time to the different disciplines. We could create opportunities for students to identify the different thinking implied at different stages. Now, this will lead to code shifting, and this can be facilitated by having those stop and breathe moments. Wait a moment, what am I missing here? Is it a principle? What is the principle underpinning this problem I'm working on right now? Is it a procedure with which I'm not familiar? Is it people in the system? Are there other possibilities here? We need to encourage fixed versus many ways of solving a problem. This will lead to sensitizing students to different kinds of contexts. We could deliberately situate the same engineering project in different types of contexts. In other words, have multiple groups working on the same project, but establish that it's for a very different kind of context in each case. We could encourage our students to interrogate the what-if implication of the projects they're working on. What if there were different social, economic, and technological variables? If we don't begin to do this, we're going to have to be accountable for more than just the current 66,000 unemployed graduates in our country. Our very survival as a society is threatened if we continue to teach as though the curriculum were neat little idealized subjects in little boxes without taking real-world complexity.